Welcome to Mythosium, the channel where we take the vastness of the universe and translate it into ideas that feel clear, grounded, and deeply fascinating. Today we're exploring a dramatic question that has captured human imagination for centuries. What would actually happen if a star exploded near Earth? It sounds like the plot of a cosmic disaster film, but the real science behind stellar explosions, supernovae, is far more intricate, more surprising, and in some ways more reassuring than many people expect. Supernovae are among the most powerful events in the universe. When a massive star reaches the end of its life, or when certain kinds of stellar remnants collapse under extreme pressure, they release more energy in a few seconds than our Sunday will emit over its entire lifetime. These explosions forge elements, reshape galaxies, and send shockwaves rippling across interstellar space. The light from a supernova can outshine an entire galaxy for weeks. Yet when considering their impact on Earth, the details matter immensely: how far away the explosion occurs, what kind of supernova it is, how much radiation is produced, and how long that radiation takes to travel across space. To understand the consequences, it helps to start with the basics of how stars die. A star is essentially a giant nuclear reactor. For most of its life, it fuses hydrogen into helium, balancing the inward pull of gravity with the outward push of radiation. As the star ages, it begins fusing heavier and heavier elements in its core: helium into carbon, carbon into oxygen, oxygen into silicon, and eventually silicon into iron. Iron is the endpoint because fusing it consumes energy instead of producing it. When a sufficiently massive star accumulates too much iron in its core, the delicate balance fails. Gravity suddenly overwhelms everything. The core collapses in a fraction of a second, and the outer layers rebound with tremendous force. The result is a core collapse supernova. There is another type of supernova that doesn't originate in a single massive star, but instead in a binary system. In these systems, a white dwarf, an extremely dense stellar corpse, draws material from a companion star. If it gathers too much mass, a runaway nuclear reaction occurs, producing a thermonuclear supernova. These explosions are incredibly luminous and play an essential role in measuring cosmic distances. Both types of supernovae release monumental amounts of energy, but the distribution of that energy and its impact on neighboring environments depend on many factors. When considering the effect on Earth, distance is everything. The universe is vast, and most supernovae occur incredibly far away. Even though they shine brilliantly from across the galaxy or from neighboring galaxies, they pose no threat. Light fades with distance, and harmful radiation weakens dramatically as it travels. The overwhelming majority of supernovae humanity has observed have been harmless, spectacular to astronomers, but irrelevant to life on Earth. Historical records provide clues about supernova visibility. In 1604, observers witnessed a bright stellar explosion that became visible during the day. In the 11th century, chroniclers documented another spectacular event that created the nebula, now known as the Crab Nebula. These events were close enough to be eye-catching, yet far enough away to be harmless. They demonstrate that supernovae can be extraordinary celestial shows without affecting life. However, the question at the heart of this topic is not whether distant supernovae are dangerous. They are not. The more interesting question is how close is too close. How near must a star be for its explosion to affect Earth's atmosphere, climate, or biosphere? Scientific models suggest that a supernova would need to occur within roughly 30 light-years of Earth to pose a significant threat to life. Even within this range, the threat comes not from the explosion itself. There is no shockwave traveling through space that could physically blast the planet, but from high-energy radiation, especially gamma rays and cosmic rays. These forms of radiation can strip away portions of the atmosphere, damage living tissue, or disrupt biological systems over long timescales. If a supernova were to occur around 30 light-years away, the initial light would reach Earth after its long journey through space, appearing as a bright point in the sky, likely visible during the day. This alone would not be harmful. But alongside the visible light, bursts of gamma radiation and X-rays would arrive. These high-energy photons could alter the chemistry of the upper atmosphere, breaking apart molecules and potentially reducing the protective ozone layer. With weakened ozone, more ultraviolet radiation from the Sunday could reach the surface, stressing ecological systems. Cosmic rays pose another challenge. These are high-energy charged particles accelerated to extraordinary speeds by the explosion. They take much longer to arrive than photons, often thousands of years, because their paths are bent by magnetic fields in space. A steady increase in cosmic rays could alter cloud formation, affect climate, or increase surface radiation levels. None of these effects would instantly devastate the planet, but prolonged exposure could interfere with biology and ecosystems in subtle or cumulative ways. To assess whether Earth is in danger, it helps to examine nearby stars. Fortunately, there are very few massive stars close enough to pose a threat. The most famous candidate often mentioned is Betelgeuse, a red supergiant located over 500 light-years away. Betelgeuse will almost certainly explode someday. It is nearing the end of its life, but it is far too distant to harm Earth. When it goes supernova, it will create a spectacular sight, possibly rivaling the brightness of the moon, but no damaging radiation will reach the planet. Another commonly discussed star is Antares, a red supergiant over 500 light-years away. Like Betelgeuse, it is destined to die violently, but it is not near enough to cause harm. Most massive stars in the local neighborhood are simply too distant to be dangerous. There is, however, one interesting case, a binary system located a few dozen light-years away that contains a white dwarf and a companion star. Systems like this have the potential to undergo thermonuclear supernovae, yet even this star system is beyond the danger threshold as far as current models indicate. Astronomers track such systems carefully, but none known today appear close enough to threaten Earth. One might ask whether gamma-ray bursts, brief but extremely intense explosions associated with certain types of collapsing stars, pose a threat. Gamma-ray bursts release colossal energy in narrow jets. If one were aimed directly at Earth from close range, it could have dramatic consequences. However, these events are rare and predominantly occur in distant galaxies where massive, rapidly rotating stars collapse in highly specific conditions. The Milky Way has the wrong metallicity for most gamma-ray burst progenitors, and no likely candidates exist near Earth. The probability of a gamma-ray burst affecting Earth is exceedingly low. The real-world risk of a harmful supernova is not zero, but it is extraordinarily small on human timescales. Over hundreds of millions of years, Earth may have been exposed to increased cosmic radiation from relatively nearby supernovae. Some scientists have investigated whether certain extinction events or climatic changes might correlate with past stellar explosions, but the evidence remains speculative. Even if such events occurred, they would have been exceedingly rare and separated by immense periods of time. Rather than posing an imminent danger, supernovae are more important as engines of cosmic evolution. When a star explodes, it creates and disperses heavy elements, carbon, oxygen, iron, and many others essential for life. The calcium in bones, the iron in blood, the oxygen breathed every moment, all of these elements were forged in ancient supernovae long before the sunday formed. In a very real sense, life owes its existence to these colossal explosions. Without them, the universe would contain little more than hydrogen and helium. Supernovae also sculpt galaxies. Their shockwaves trigger star formation by compressing surrounding clouds of gas. They enrich interstellar space with elements, influence magnetic fields, and help shape the structure of spiral arms. Far from being merely destructive, they are integral to the cycles of creation and transformation that define galaxies. If a star were somehow to explode extremely close to Earth within a few light-years, the outcome would be severe. The radiation would be intense enough to strip the ozone layer almost entirely. The ultraviolet radiation that reached the surface would be harmful to organisms. Atmospheric chemistry could be dramatically altered, leading to climate disruptions. This scenario, however, is extraordinarily unlikely, because there are no stars close enough to Earth that are capable of undergoing such an explosion within the foreseeable future. A core-collapsed supernova must come from a star at least 8 times the mass of the Sunday, and no such stars exist within the dangerous radius. Many of the nearest stars are low-mass red dwarfs and capable of producing supernovae. The nearest massive stars are hundreds of light-years away, far beyond the threshold of danger. Humanity lives in a relatively calm region of the galaxy. Fortunate placement from a cosmic safety standpoint. The Sunday itself cannot become a supernova. It lacks the mass required to initiate core collapse. Instead, it will eventually become a red giant, shedding its outer layers and then contract into a white dwarf. This transformation will affect the solar system billions of years from now, but it is unrelated to the violent processes that generate supernovae. Even when considering the rarest and most extreme types of stellar explosions, Earth's position remains secure. Massive hypergiants capable of producing especially powerful supernovae are located far away. Gamma-ray burst progenitors require very specific stellar conditions absent in the Milky Way's current environment. And potential white dwarf explosions, while dramatic, occur at safe distances. Understanding this provides perspective. The universe is full of dramatic events, collisions, collapses, bursts of radiation, but Earth occupies a remarkably stable niche. This stability is part of what allows life to flourish. Yet studying supernovae remains crucial, not because they threaten Earth, but because they illuminate the life cycles of stars, the origin of elements, and the dynamics of galaxies. They are windows into the physics of matter under extreme conditions. Their study also deepens understanding of cosmic time. Supernovae mark the ends of stellar lives and the beginnings of new cycles. They remind us that the universe is not static, but constantly evolving. Humanity's existence depends on the long chain of stellar generations that preceded the Sunday. Each supernova contributed to the material tapestry of the solar system, and shapes the environment into which Earth was born. So what would happen if a star exploded near Earth? In reality, nothing of the sort is expected. The nearest candidates are far away, and the cosmos is vast enough to protect the planet from the worst dangers. Yet the question remains fascinating because it invites deeper exploration into how stars live and die, how galaxies evolve, and how life emerges from the debris of ancient explosions. In the end, the story of supernovae is not a story of destruction, but one of cosmic renewal. These explosions enrich the universe with the ingredients needed for planets, oceans, and life. They are violent, spectacular, and essential. Without them, the world would not exist. At Mythosium, we explore these cosmic stories because they offer a broader perspective on humanity's place in the universe. If you enjoy learning how the extreme events of the cosmos shape the most familiar aspects of our world, make sure to subscribe. There are countless wonders waiting to be uncovered, and together we'll continue exploring the mysteries at the edge of human knowledge. Thanks for watching, and stay curious.